Right, just want to do a video about variable acceleration and vectors because I can't remember doing it actually, and again, it's another one of those gaps. And I've got 4 examples here. I'm going to do work solutions, which I'll print in the way I've been doing with other examples, but I'm also going to work through them in this video, so you can choose how you consume them. Now, again, this is one of these things I don't think is going to come up because it mentions vectors on the pre-release under constant acceleration, but then variable acceleration doesn't mention vectors. But there we go, we can't assume anything. So what I've got here is a standard non-vector variable acceleration question. All right, so this is the sort of question I think is going to come up, and I've still got this nagging thing at the back of my mind that I'm not sure we've done, that there was any, or you perhaps could have used it, but integration by substitution didn't really feature much in the first 2 pure papers. So I'm just wondering if, I don't know, they might throw in a nasty integration by substitution. Anyway, this is not an integration by substitution example. So just a reminder, acceleration, velocity and displacement are related, and I can differentiate to get between them and integrate to get between them. So in this question, we're given a velocity, an equation for acceleration, not constant. So constant acceleration, we just use suvat. Not constant, this is clearly a varying thing. So we are asked to find an expression for the velocity, the maximum speed and the distance travelled. So this is going to involve integrating twice, because I want to integrate to work out velocity and then integrate again to work out distance or displacement. Okay, so I'm going to integrate my formula with respect to t. So cos, when you integrate, becomes sine. So cos of 2 pi t becomes sine of 2 pi t divided by what you get when you differentiate the bracket, which is 2 pi. Mustn't forget the plus c, and that's crucial. I need some values to substitute in to get c. So we're told about the velocity at time 0. So substitute those in, and that gives me 1 over 2 pi. Sorry, you may choose to pause the video and work through it yourself and then look at this. I'll leave it up to you. So that's my formula for velocity. So that's the answer to part A. And that's velocity in meters per second. I'm going to be careful with units because this is one of the few places with differentiation integration where there is a unit, isn't there? So we've got meters per second squared and meters per second for velocity. The maximum speed, well, if I look at this equation, sine of anything will never get bigger than 1. So that's going to be 1. So then at its maximum. So the maximum velocity will be, when that's 1, so you get 1 over 2 pi plus 1 over 2 pi, which is 2 over 2 pi, which is 1 over pi. So that's the maximum value of speed. And that was, I used common sense there. That wasn't any sort of, integration, differentiation or turning points. That was just looking at this and saying, right, that's common sense. We're then asked for the distance travelled in the first 3 seconds. So I've got my formula for velocity. That was from part A. And I just note that I've got a 1 over 2 pi in both cases. So I pull that 1 over 2 pi out. And 1 over 2 pi is a constant. So that means when I now come to integrate the velocity to get distance, I can have that 1 over 2 pi out the front. And we want the distance in the first 3 seconds. So I'm going from 0 to 3. So that's the thing I'm integrating. Sine, when you integrate, becomes minus cos. So sine of 2 pi t becomes minus cos of 2 pi t divided by what you get when you differentiate that, which is 2 pi. When you integrate 1, you get t. So there we go. The c's cancel, substitute values in. Okay, it looks horrible, but it actually falls out quite nicely because that is minus 1 over 2 pi, and that is minus 1 over 2 pi, but minus that. So those two cancel out. So you're just left with 3. So you get 1 over 2 pi times 3. So that is the distance travelled. So that is a variable acceleration question that doesn't involve vectors. It still involves some pretty tricky and fiddly integration in this case. We could well get one that involves differentiation, moving the other way up the relationship between distance, velocity and acceleration. Right, let's now look at a vector one though. Okay, so here is a question where we are given a formula for displacement distance. Position vector means where it is, so it's distance. So they're using r rather than s, I don't know why, but remember, the relationship between distance, velocity and acceleration, well, that's, we differentiate to get between, to move up that ladder, don't we? So in this question I need to differentiate to get velocity and differentiate to get acceleration, but the distance is given as a vector. And I know that I've always said, right, I find it a lot easier to write that distance vector in a column. So this would be however, I think this is the only occasion where it's probably easier to leave it in I and j notation, because to differentiate this expression, all we need to do is to differentiate the I and the j separately. Now you could say, well, that's easy, I can do that there as well, and brilliant, fine. That's absolutely fine, no problem doing that at all. But whichever way you do it, you just differentiate the I part, so this expression we can easily differentiate, and the j part, this expression we can easily differentiate separately. So you may want to pause at this point and have a go at the question, or you might just want to carry on following through my explanation. So again, a bit confused as to why they're using r rather than s or d for distance, but there we go. So to find the velocity, I just need to differentiate this. So I differentiate that, 3t minus 4, I mean that's a really easy differentiation, you just get 3, and this becomes 3t squared minus 4. So that's my velocity, and that's in meters per second, isn't it? I'm then asked, what's the velocity when t is 3? So I just substitute t is 3 into this. Obviously that doesn't change, and that becomes 23. Now, that is the correct answer. Brilliant. All right, because it asks for the velocity. That's the correct answer as well, if you chose to write it like that, although I always say if they use IJ notation in the question, make sure your final answer is in IJ notation. If it had asked for the speed, remember that's easy to work out. The speed is just the magnitude of that vector, so it's 3 in the x direction, 23 in the j direction, so so we'd work out that using Pythagoras. And the direction of travel comes from the velocity vector. It's a really important point. So if it had asked for something about the direction, then you just work out the angle using that. It doesn't in this question, so actually that's all we need to do. And then the acceleration, well, this was my formula for velocity. Not this, that's the specific value of velocity when t is 3. This is the formula for velocity, so I just differentiate that again. So 3, when you differentiate it, becomes nothing, and 3t squared minus 4 becomes 6t. That's my formula for acceleration. That's meters per second squared, and it asks what do you get when t is 3. So that becomes that, which I would probably just write like that. I don't think I'd bother writing the 0i. And that is that question, simple as that. Okay. Okay, so here's another question that requires differentiation. Again, we're given displacement in terms of r, seems to be a convention in this book. Perhaps that's what this exam board uses. And we're asked about something about speed and something about acceleration. So this is going to involve differentiating twice. So there's my distance, so I differentiate it to get my velocity equation, so that becomes that, and k is a constant, so that just becomes 2kt. But we're told that when t is 2, the speed, not velocity, the speed is 16. So if I make t equal to 2, this becomes this. So that works out to be minus 4, and that works out to be 4k. And so minus 4k, are we told k is positive? Yeah, k is positive, so I know it's going up. So I know that the speed, the magnitude of this line is 16. So I just use Pythagoras. That squared plus that squared has to equal that squared. And that gives me the value of k. Again, don't have to worry about plus or minus because we're told in the question that k is positive. So I know the value of k, so I can rewrite this now as 2 root 15t. Okay? Now we're asked in part B to find the acceleration of p at the instant when it's moving parallel to j. So this is a question where I'm not going to leap to differentiate straight away, because I'm going to work out when is it moving parallel to j. Now j is a unit vector in the direction of the y-axis. So this is a key thing. Parallel to j means it's moving in this direction, so there's no x component to its velocity. Velocity tells us the direction. So this is our formula for velocity, although we now know that this is root 15. This, if it's moving in that direction, or down, parallel to j, could be up or down, it means this would have to be 0. So that's my first step in this part B, is I work out when does the x component, the horizontal component of speed, here, when does the horizontal component of speed equal 0? And I'm leaving it in a surd form. Okay, so that's the time. It wants to know the acceleration at that time. So remember, we've got our formula for velocity here, but we now know that k is root 15. So differentiating that just gives me minus 12t, and so that's 2 root 15t, which just becomes 2 root 15. Substituting t is root 30 over 3, and get my answer. Acceleration as a vector, meters per second squared. Did I need to leave it as surds? Again, I think surds are always better, and we've got calculators that deal with them. But belt and braces, if you really want to, you could then write rounded values underneath. Okay. Okay, here's a fourth question. It's drizzling outside, so I can think of no better way of spending a Saturday morning than doing some sums. Again, you might want to pause and have a go before I work through it, or you might just want to follow through, or you might just want to work through the printed sheets yourself once I send those to you. Right, so here we are given a formula for acceleration, and we are asked about, we're told something about velocity, and we're asked something about distance. So again, this looks like a question where we're going to have to integrate to get velocity and integrate to get distance. So we've done a couple of questions where we're differentiating, now we're integrating. Same principle, we integrate the I and the j parts separately. Part A is about the direction of motion. That comes from velocity. All right, direction of motion we get from velocity. So the first thing I'm going to do is to integrate my acceleration formula, and that gives me this. C is a vector. Okay, it's not a number, not a scalar, it's a vector. So I've got to work out what c is, and I'm told that when t is 3, the velocity is just 6i. So I substitute that in. So this is my formula for velocity, so I make that equal to 6i, and then I replace my t with 3, and then we can do algebra with I and j, so I take 12i from both sides, giving me minus 6i, and I add 9j to both sides, giving me that. So I can now rewrite this formula as a velocity formula, and this is a key step. So this is my original formula, this is my c. I can combine the two I bits, so I've got 4ti minus 6i, so I'm writing that like that. And yeah, be careful here, I've got a minus t squared j and a plus 9j, so I chose to write that as plus 9 minus t squared j. Okay? Now the question says, what's the value, the question says, what's the angle between the direction of motion and I? So I, remember, is a vector going in the x direction. So they just say, what's the angle between this and the horizontal? So I take my brand new velocity equation and I make t equal 2, which makes it look a whole lot simpler, and that gives me the direction. So the direction is 68.2 degrees above the I vector. So that's nice and straightforward. The only fiddly bit is the working out of c, doesn't it? Okay, so part B, the distance of p from the origin. So having integrated acceleration to get velocity, if I now integrate that again, I get displacement, its position relative to some fixed origin. So that's what I'm going to do. I'm going to take my velocity equation, the one including the value of c, and I'm going to integrate it to give me, well, I've adopted their notation using r for displacement. So that integrated gives me that integrated gives me that, plus c, and then I thought, well, I've already used c, so I'm going to use a different letter. Doesn't really matter. I then go through that same process we went through with the velocity equation. This is a vector, and I'm told in the question that when t is 3, the position vector r is that. So I take that equation and make r equal to that, and I substitute t is 3 into this, and it gives me this, and then I, well, take away 0 i's, so I'm just left with the 20i, take away 18 j's, 3 take away 18 is minus 15. So that's the constant. So then I can rewrite this, replacing that with 20i minus 15j. This is a bit fiddly, looks a bit unpleasant, but there's a quick and happy ending to this question. So that's the original displacement equation, that's the new value of the constant k, and then I can just wrap it all up. So these are my I terms, so that gives me that, and then I've got j term, take away 15, so that gives me that. And then the question says, go back to the question, sorry, sliding around a bit, I'm not feeling dizzy. The distance of p from O when t is 0. So this equation gives me the position vector, its position horizontally and vertically from the origin. So when I make t equals 0 in that, it all falls out to be this, and that means that its position vector, remember this isn't telling us about the direction, velocity tells us that, this tells us where it's actually got to. So this is the origin, it's gone 20 in that direction, 15 in that direction, so its distance is, using Pythagoras, 25 meters. Okay, final question then. Here we're given velocity and we're asked about position. So that's going to be integrating again. You might want to pause the video and have a go first, or you might just want to work through this with me. So I've got my velocity formula, so I'm going to integrate that to get an expression for displacement, or the position vector. And I'm told where it is when t is 0, so that allows me to work out the value of c. Remember, c is a vector, that's meters, that's the units. And unsurprisingly, if that's where it is when it starts, that is the value of c. So that allows me to work out that. So I can rewrite my formula from here like this, just replacing c with 2i minus 4j and then rolling it all into one expression. So that's part A. We're then told about a second particle which is moving with constant velocity. So this is variable, it will vary according to t. This is constant velocity. We're in a sort of Suvat situation with this one. And I've got a formula for the position of the first one, p, so I'll call that rp. Just done that through integrating. I'm going to use a bit of common sense now for the position of the second particle, particle q, and I'm going to go back to column vectors here. This is where it starts, and its velocity is this many meters per second, and that tells me how far it's travelling in those two directions every second. So I can actually write a sort of common sense formula for its position. In terms of its x displacement, it starts at 2 and every second it moves 8 meters further away. So its x displacement will be 2 plus 8t, and in terms of its y displacement, starts at 0 and every second moves 4 meters away, so its y displacement will be 4t. So I've got two formulas, one for the position of p and one for the position of q. I'm asked to find, or I think I'm asked to prove that they collide. So they will collide if that ever equals that. So there we go, I'm going to write that down. They will collide if the position of P ever equals the position of Q. And here's where we throw in one of our key techniques, that is equating. We used it with vectors at pure. Looking at the i's, on this side, that's how many i's I've got. And on this side, that's how many i's I've got. So if they collide, there will be some point where that equals that. Sorting it all out, I get an expression here. Don't divide by t, remember, because that will lose that solution. But we're not worried about when t is 0. This is going to be t minus 4, t plus 4. So its solutions are t is 4 and minus 4. We're not worried about minus time. So the I displacements of the two particles are the same after 4 seconds. So let's now equate, going back to the original one equals the other equation, let's equate the J displacement. So that equation gives me, well, I could solve it to get t is 4, or I can just substitute t is 4 in and find that it's the same. So I could have taken away 4 from both, so I've taken away 4t from both sides and added 4 to both sides to show that t is 4 is also the place where the J displacement's the same, or I could just substitute t is 4 into it, which was the time I'd already worked out was when the i's were the same, and find they were the same. So that's proved that the particles collide after 4 seconds. Okay, so whether it's in without vectors or with vectors, variable acceleration is all about differentiating and integrating.